morning, my dear students. Welcome back after the vacations. Before the vacations, we had completed two lessons, that is force and the second one Gauss's theorem. Now, as you all know, the syllabus is too large and we have to complete it before the end of the year, that is before January, before your pre-boards. So we will rush up with the syllabus, keeping in mind that you understand the syllabus. So please follow the videos that are being sent so that you can understand the lesson. Okay, so today we shall start with the third lesson, electric potential. As you all know, when we talk about the electric charge at a given point has got two parameters. One, the electric field intensity. The second one is the electric potential. So, at any point around the electric charge, there is an electric field that can be calculated. What is electric field? It is the force experienced at a point due to an electric charge. What is electric field? F is equal to QE. So electric field is the force experienced by test charge at a given point. It is a vector quantity, and vector quantities, you know that they have got directions. So to calculate the intensity due to different charges at a given point, we need to use vector methods. Whereas the second parameter is the electric potential. Now what is electric potential? We are going to study electric potential. So electric potential, it is the amount of work done in bringing a test charge from infinity to a point in the given electric field. It is the amount of work done in bringing a test charge from infinity to a given point in the given electric field. Okay, the reference point is taken outside the field where the potential is taken 0. Okay. So electric field is a vector quantity, electric potential is a scalar quantity. Now we have the definition for the electric potential. The work done by an external agent in carrying a unit positive charge from infinity to a given point in the electric field is called electric potential at that point. It is the work done in carrying a unit positive charge. It is the work done by an external agent in carrying a unit positive charge from infinity to a given point in the given electric field. So work, W is work here, and Q naught is carrying a test charge. Q naught is a negligible test charge. So electric potential is the amount of work done in carrying a test charge from infinity to a given point. Okay. So SI unit of electric potential is volt. 1 volt is equal to 1 joule per coulomb. 1 volt is equal to 1 joule per coulomb. So now we find out the dimension of volt. Joule ml square T raised to power minus 2. Joule is force into displacement. So ml square T minus 2. Coulomb is current into time, A into T, ampere into time. So the dimension for volt is ml square T raised to power minus 3 A raised to power minus 1. This is the dimension of electric potential. Then we have physical interpretation of electric potential. We know that a liquid always flows from a higher altitude to a lower altitude. The heat or the energy or the heat energy flows from high temperature to low temperature. Similarly, the charges also flow from high potential to low potential. The charges also flow from high potential to low potential, and when the charges flow, it makes current. So the current is always flowing from high potential to low potential. So physical interpretation of the potential is to determine the direction of the current. So positive charge always flow from high potential to low potential, while the negative charge always flow from a lower to a higher potential till the potential becomes equal, or till both the surfaces are at equipotential. For the electric potential, the earth is considered as the reference point. It means that the electric potential of the earth is taken as 0 and is not affected no matter what large charge is taken from the earth or given to the earth. Okay, for the reference point we consider earth to be at a 0 potential. Whatever amount, any amount of charge can be given to the earth or any amount of charge can be taken out from the earth. All points where electric field does not exist, electric potential is 0. Is it clear? All points where electric field does not exist, electric potential is taken as 0. The next point that we are going to discuss is potential difference. So, potential difference is to be calculated. So, in the definition of potential, we have said that the potential at a given point is the amount of work done in bringing a test charge from infinity to a given point in the given electric field. So, let us consider the potential due to a charge. Now, first of all, we have to have a charge plus Q naught. We are talking about potential difference. Potential difference. So we have a charge Q. It's not a test charge, it's a charge plus Q, and it will have an electric field around it. Okay? So it will have an electric field around it. So we consider a charge that is at infinity Q naught. It is being brought to a point B in the electric field of this plus Q charge. So we have brought a charge at the point B here, and then it is further taken towards a positive charge at E. Is it clear? So a plus Q charge has got an electric field around it, and we bring a test charge Q naught from infinity to a given point towards the plus Q charge. So it will have potential at V. So this is the potential. Potential at V is VV. Potential at A is VA. Now, when we are bringing the charge particle from infinity to a given point, naturally, when we bring it up to this point, the potential will be different. Here to point A, potential will be different. The difference of the two potential is known as potential difference. VA minus VB. This is potential difference. Potential difference is equal to VA minus VB, and that is equal to till here. If we are bringing a charge particle, the same amount of work will be done if we bring the particle towards B or to A. Up to this point, the amount of work done will be equal from infinity. So, what is the difference? The difference is only the amount of work done from this point to this point. Okay? And we are bringing the charges from infinity to a given point up to the B point. The work done will be the same. Okay? Suppose we are taking two charges, both are brought. One is to the point B, another to point A. Both will do same amount of work up to B. What will be the difference? Difference will be from B to A. So that is the work done in bringing a charge particle from B point to A point in the given electric field. So VA minus VB equal to W upon Q naught. Is it clear? Potential is a scalar quantity. Electric potential is a scalar quantity. If you bring a test charge, positive test charge, if you are bringing a positive test charge from point B to point A, then work is to be done by an external agent. Work has to be done. Why? Because we have the particle Q naught, which is a test charge, and here positive charge. So there will be a repulsive force. So some external work has to be done against the repulsive force. Then only the particle can be brought towards the plus Q charge in the given electric field. So some work has to be done by the external agent to bring the test charge particle in the given electric field of positive charge. So work is done by the test charge. So potential at the point A will be higher than the potential at point B. Now suppose this is negative charge. Suppose we take it as negative charge. What will happen? Negative charge. The test charge is positive. The test charge is positive, then what kind of force will be there? The Coulombian force will act. That force will be attractive force, because the two charges are opposite to each other. The two charges are opposite to each other, minus q and plus q. So what will happen? The test charge will be pulled by the minus q charge in its electric field. At this point, the work done at B will be greater than work done at A. Is it clear? Work done at B. So potential at B will be greater than potential at A. Now we will derive the formula for the electric potential due to a point charge. So let us take our plus q charge at the point O. There is a positive q charge at the point O in a medium of dielectric K. So this is not in here, it is in any other dielectric medium whose dielectric constant is K. Let us take a point P at a distance r in the electric field of this positive charge plus q. Okay, so P is a point at a distance r, and we must calculate the work done in bringing a test charge from infinity to a given point P. So we will calculate, this is infinity, we are calculating the amount of work done in bringing a test charge from infinity to a given point. It's not minus, it is from infinity to a given point. Okay, so Q0 charge is being brought from infinity to a point P. For this, we consider the charges, a Coulombian force that is acting on the test charge, or between the test charge plus Q and the charge Q, Q0 and Q. So force experienced by the test charge Q0 is given by the formula Coulombian law 1 upon 4 pi epsilon naught Q0 upon x square, the distance. So we are considering the particle is at the point A. The distance of the particle to the point A is x. So the force experienced by the test charge Q0 at the point A is given by the formula 1 upon 4 pi epsilon naught 1 upon 4 pi epsilon naught K Q0 upon x square. Okay, the direction, now since this is a positive charge, the test charge that has come to the point Q0 in the given electric field is also positive. The force will be away from O, because it is a repulsive force. So direction of the force will be away from the force. Now we have to displace the particle to a very small distance. The small distance from point A to point B. Let the small distance be dx. Okay, small distance is dx. So we are doing work against the force that is acting. So the displacement is against the work. So we have minus dx. Now we will calculate the small amount of work done in moving a test charge Q0 from the point A to point B. It is moving against the force. So dW is equal to F dot minus dx. Now we integrate both the sides. And we find out the work done from the point A to point B. When we bring the test charge from point A to point P, the amount of work done. So initially we were finding out only from A to B. So then the formula was F minus dx. Now we will find out the work done in bringing a test charge from infinity to the point P. So the lower limit is infinity, and where are we bringing? We are bringing at a distance of r. So the upper limit is r minus f dx. Okay, we substitute the value of f 1 upon 4 pi epsilon naught q0 upon x square. So all of them are constant. 1 upon 4 pi epsilon naught q0 are constant, so they have come out. The integration will be done of only 1 upon x square dx. On integration, we find that W is equal to 1 upon 4 pi epsilon naught q0 upon r. We know that electric potential is equal to W upon q0. So V is equal to 1 upon 4 pi epsilon naught q0 upon